is starting the debugger. As I mentioned, there's a few different ways to do that from the command line, so we'll go through some of the more popular ones right now. The first and most useful command that you'll be using, and the one that you'll probably reach for the most in your day-to-day development, is delve debug. So the debug subcommand does a lot of things. So you would run this command in essentially where your main package is by default, or you can also provide it a package path. But if you run it in the directory where your main package is, this simple command does a lot of things for you. So by default, it will compile your program for you, and it'll compile it in such a way that it's optimized for debuggability. So by default, the Go compiler will provide will automatically use a bunch of like optimizations and things like that when compiling your program. When Delve invokes the Go compiler, we pass a few flags along to disable that some of those optimizations, so that like some of the optimizations are like inlining of functions and things like that. These are things that it just taking them out produces a binary that's more, like I said, optimal for debugging. So the flag that we provide, that we pass to the Go compiler, is -gc flags all -n-l. And you can find a little bit more about that information if you do like Go help build about what those flags do. But essentially, it turns off some common optimizations that have a tendency to trip up debuggers sometimes. So once you do all that, as I mentioned, Delve will compile your program. It'll start running it for you. It'll automatically attach to it, and then it'll land you in a debug session, ready to go, ready to start inspecting your program. The next most useful subcommand that you'll likely use is delve test. So this does almost the same as the debug command, except for this will compile a test binary for you and start debugging that. So if you're working on something that maybe doesn't have an actual executable, like maybe you're just working on some library code or something like that, or maybe you're just working on a very specific feature that you would like to debug, hopefully you're writing tests along with your software. So you can use this subcommand to debug your program within the context of the tests that you're running. So this can be super helpful, like I mentioned, for like library code and things like that, where you don't have a main package, or if you just want to kind of scope down your debug session, this is a good way to do it. The next most common one will probably be exec. So if you already have a pre-built binary on disk, you can use DLV exec to run it. The caveat being, as I mentioned, when you use delve debug, we pass a few flags to make the binary really optimal for debugging. So in this case, your mileage may vary. We've done a lot of work both with Upstream Go in the compiler and linker and within Delve to be able to debug just regular binaries built with Go build without any special flags or anything like that. So debugging an optimized binary is still a very viable way to go, and even more so now with a lot of the work that we've done in the compiler linker to kind of get some more of the debug information built into the binary and within Delve itself. So if you have a binary that you already have on disk, or maybe something that you're running in production, this would be a good way to debug it. Another common subcommand you're going to want to use is attach. So if you already have a program that's running on your system, you would just want to attach to it and start debugging it, this would be the subcommand you're going to want to use. So you just write delve attach, and then you provide the PID, and Delve will take care of the rest, attaching it and kind of going into a debug session for you. The next useful subcommand is trace. This was one of my personal favorites, and one that's gotten an overhaul recently to make it a lot more efficient. This will be the delve trace subcommand. So essentially what you do is you provide you can provide a regular expression, and what it will do is delve will set a breakpoint or a trace point on any function that matches that regular expression. And when that trace point is hit, delve will output what Goroutine hit that trace point, the function that was hit, the arguments to the function, and also the return arguments to the function as well. So this is a really useful subcommand for if you don't want to jump into a full-fledged debug session, like an interactive debug session. You just kind of want to spy on your program a little bit. This is the ideal way to do it. And as I mentioned, the trace backend within Delve for the next release, we'll be getting a huge overhaul to make it a lot more efficient, especially mostly on Linux for right now, using eBPF probes. If you're not super familiar with that, I don't think I have enough time to go into that topic during this presentation, but I would encourage you, if you're interested, to look into a little bit more about the eBPF functionality in the Linux kernel. But Delve is using that now to overhaul the tracing backend to make it more performant enough to the point where you could actually trace programs that are running in production without too much overhead and bringing down production systems and things like that. It makes it a lot more viable. So all that to say, this is one of my favorite commands and something that I use quite often to just kind of spy on programs a little bit. Let's see. Okay. A few additional commands that we have that you likely won't use very much, delve dap and delve connect. So delve dap starts a dap server, which is short for debug adapter protocol. It's mostly used for IDE integration, so likely not something that you will use. The other one is delve connect. So this one you might get a little bit more mileage out of as a day-to-day user. It allows you to connect to a remote Delve instance. But something to note, the connection is not secure. We don't do any kind of like TLS or transport layer encryption or anything like that through the connection. So it's recommended to try to connect over like an SSH tunnel or something like that to secure the connection. But essentially, this allows remote debugging. And we'll get into this a little bit with the demo at the end, but just something to kind of keep in the back of your mind if you need to do some, if you want to do some remote debugging, and you need to connect instead of being directly on the machine to run Delve. This is another option. Okay, so now let's talk about a little bit, like we're in a debug session. What do we do now? So let's talk a little bit about setting and using breakpoints. First of all, I want to talk a little bit about what is a breakpoint. So a breakpoint is essentially, it's implemented in various ways, but it's either an assembly instruction or a special register. But it's essentially a point at which when a program is attached with a debugger, if the program hits this special instruction or this special point, which is a breakpoint, it allows the program to stop for a second and transfer control back to the debugger to do whatever it needs to do, and then the debugger can go ahead and continue the breakpoint from there, or continue the program from there, rather. So let's talk about how to set breakpoints from within a Delve debug session. The most useful way is just setting a breakpoint directly on a function. So here we can say we want to set a breakpoint on main, which that's the kind of the main entry point of your program from your point of view, right? This is the main function that you wrote, specified by the package path as well. So this is a useful way of, if you know the function name and the package path and everything like that, this is a really useful way of setting a breakpoint, and probably one of the more common use cases. So you can see some of the output there. It tells you the breakpoint number, the address that it was set at, the function, and the file and line that address and function and everything corresponds to. Now, Delve does a little bit something a little bit special for breakpoints with Go that I want to talk about. So when we say something like this, like set a breakpoint on main, most debuggers will set a breakpoint on just the first instruction of the function. That doesn't work as well for Go because Go functions actually have a prologue which kind of check the size of the stack, that does some kind of bookkeeping to make sure that the function is going to have enough stack to execute. Because if you're not aware, Goroutines typically start with really, really small stacks and grow over time. This is how they're easier to create and more efficient than true operating system threads. So at the beginning of a function, kind of checks to make sure it has enough stack. If it doesn't, it'll grow the stack, copy over to it, and then perform that check again. So what you can see from the perspective of a debugger is if you set the breakpoint instruction on the first instruction, you can see kind of like a stuttering where it looks like you're not actually moving forward, but you really are. So what Delve does is it's smart enough to set a breakpoint after that prologue so you don't get that kind of stutter effect as you're stepping through your code. And that's just kind of one of the ways that Delve being a Go-specific debugger, we can do those kinds of things where we can take into account some of the nuances and kind of change, like non-standard things that happen in Go and still provide the best debugging experience for users. So another way to set a breakpoint is specifying a file line. So here we can see main.go and line 15. The syntax is pretty self-explanatory. And again, you can see a breakpoint was set, and you can see that it was set on that file and line. Another way to do it is you can set breakpoints at just raw memory addresses. So this is the syntax for it. It's kind of like dereferencing a pointer. And then with that, you can see the breakpoint was set, and you can see it was set specifically at the address that we requested. And then we get also, all the other information, the file line, the function associated with it, and all of that stuff comes from the output as well. Another way to set a breakpoint is similar to what happens when we talked about the Delve trace subcommand. So you can provide kind of like a regular expression, and Delve will set a breakpoint on any function matching that regular expression. So you can see here, we only had one other function there, main call me. So that's the only other function in the main package besides main, which we've already set a breakpoint at. So you can see it was set there and the information for it as well. So this is useful, like if you want to just spray a bunch of breakpoints within like a package or a specific series of functions or something like that. This is just a convenient way to do so. You can see, yeah, it kind of goes on. It's adding a few other things as well. Let's see. Okay. Another option that I'd like to talk about is another cool way to set breakpoints is if you want to just set a breakpoint directly in the code as you're writing it. The Go standard library does provide this function. It's runtime breakpoint. And basically what it does is it intentionally will execute the breakpoint CPU instruction. So this is, and Delve is smart enough to know when it's in this function to step out of it and kind of put you exactly where you want to be. So when you set a breakpoint this way, from the perspective of your debug session as you're going through with Delve, you'll end up on whatever the next source line is after this line. And this is useful for like if you're just in your editor writing code and you're like, especially maybe if you're using it through an IDE and you don't want to click on the line number to set a breakpoint, or if you're using it without an IDE and you don't want to like remember like the file line or whatever to set a breakpoint. If you just type runtime breakpoint in your source code and execute it under Delve, Delve will stop and respect that breakpoint. One thing to note, though, if you keep this code in and you're not running under a debugger, your program will crash. It will fatally panic. So just something to keep in mind. be careful with this one. Okay, so let's get into a little bit more advanced stuff about breakpoints. So let's talk a little bit about assigning behavior to breakpoints. And this is mostly like a convenience thing. If you're in a debug session, this functionality will just kind of make some repetitive things a little bit easier for you. So if we set a breakpoint and we name it, so break also accepts another argument which allows you to assign a name to a given breakpoint. So we're saying break on the function main, and let's call it main. So break main. Kind of stuttery, but gets the point across. We can see the breakpoints there, the output we get. Now we want to assign some behavior to it. So we want to execute the stack command every time the breakpoint is hit. So the syntax for that is on, and then the name of the breakpoint, and then the delve command that you want to execute every time that breakpoint is hit. So in our situation, we say on main stack. When we continue to the breakpoint, we can see we've hit the breakpoint, and we get a stack trace printed out. So the stack command will print a stack trace from wherever you're at. And with this syntax, now anytime we hit that breakpoint, we'll get a stack trace printed out. This is useful for, like I said, if you're doing a lot of repetitive stuff, maybe every time you hit a breakpoint, you run maybe like a series of commands, or you always run a specific command. This is just a convenient way to not have to type that every single time to make the debug session go a little bit more smoother. Another thing that we can do that is really useful is assign conditions to breakpoints. So again, we set a breakpoint on a specific location, and we call it loop. We get the output there. Then we assign a condition. We want to say con loop I equals 3. So to break down the syntax a little bit, we're saying con, which is saying like set a condition on the loop breakpoint, so the breakpoint named loop. And then following that, you give an expression. And the expression is evaluated in the context of where you stop in that breakpoint. So if you have an iterator variable in a loop named I, we can say, I want to stop anytime that value is equal to 3. And then I want to print the value of that. So like we just saw with assigning behavior. So anytime that breakpoint is hit, I want to print the value of it. So we continue, we hit the breakpoint, and then we see the output there of the print. We see I is equal to 3. And then we get just a little bit more output there. But we can see that we continued, and we only stopped in that breakpoint when that iterator, when that variable was equal to the expression. So the expression that you give it has to evaluate to a Boolean. But it's just a really, really useful way for, like, if you're debugging a loop or something that only happens under specific circumstances, you don't have to continue past a bunch of breakpoints that you'll end up ignoring. This is just a convenient way to get just directly where you want to be. All right, let's talk through a little bit of some other breakpoint commands. So if you want to list all breakpoints, just write breakpoints. It'll list all of the ones that are set. And by default, you'll see some that you didn't explicitly set. Delve will automatically set some convenience breakpoints for you for runtime fatal throws and panics. This is just so that, like, if the runtime crashes or your program panics during a debug session, we can capture that, and you'll be stopped right at the beginning of the panic, so you can inspect your program state before it actually exits. You can clear all breakpoints very easily with just clear all. You can clear a specific breakpoint by saying clear breakpoint ID or specifying the name. And you can also toggle a breakpoint. So similar, by name or ID, you can toggle a breakpoint on and off. This is useful if you don't want to completely remove it. You just want to kind of ignore it for a little bit and then maybe re-enable it later. All right, now that we set breakpoints and we know how to tell the debugger where we want to stop, let's talk about how we can control program execution so we can hit those breakpoints. So the first most useful thing that you'll probably want to do is use continue. So continue continues program execution, as you would expect. It will stop at a breakpoint and certain signals and program exit. Also panic and things like that, as we saw. A cool convenience feature of this is it can accept a location to continue to, which I'll show a little bit later. So here, if we want to continue to an existing breakpoint, we set a breakpoint, we just continue to it, and then you can see in the output there that we've hit that breakpoint. We get some output there. If you want to take all of that into a single command, into one single step, you can continue directly to a location by just saying continue main.main. So if you don't want to set like a recurring breakpoint there that persists through your session, you can just use this to continue directly to someplace in your code, a function or something like that, and then not have to worry about toggling a breakpoint off or clearing it later. I use this feature a lot in my personal debugging, actually. So the next one that we're going to talk about is a command called next. So it continues programs to the next source line. It steps over function calls. So we'll talk a little bit how to step into function calls shortly, but this specific one steps over. It will stop at breakpoints during the next operation. And it also accepts a number. So if you wanted to step over like the next 5 or 10 lines, you can do that with the provided syntax. So stepping over a single line, we continue to a specific location. We see, we're at line 14, the beginning of the function. We execute next, and now we see we're at, instead of line 14, we're at line 15, and we're at the first kind of piece of code within that function. If you want to step multiple lines, you just provide a number, and then you can see we've stepped forward multiple lines. We're not going directly to 18 just because of how the source code was laid out, but you can see we've moved forward a couple lines since we were on 15. The next most useful kind of execution manipulation commands that you'll use is step, step out, and step instruction. So step continues to the next source line, but unlike next, it will step into functions. Step out will continue until you return from the function that you're currently in. And as a convenience, it'll show any return values of that function for you. Step instruction will do just kind of what it says. It will continue to the next CPU instruction. So it will literally just step one CPU instruction. So we'll continue to a location. You can see we're here kind of at the call point of this function. If we call step there, now we can see we're within that function. So instead of stepping over it, we step into it, and now we can explore what's going on in that function. Okay, so we're in there. We've done what we need to do. We want to get back to the context of our caller. So we call step out, and then we can see now we're back at main, and we can see the return values of the function that we called. And we're back kind of, at the return value. So we're back at the call site, but at the specific instruction that it would return to. Now, if you want to step just a single CPU instruction, just use step instruction. You can see the example doesn't give a lot of output there, but if you were doing this and if you were doing this through normal code, like you're not actually stepping through assembly code, you can see the PC value there, which is the program counter, which is basically the address of the instruction that you're executing. You would see that increment. This is really helpful if you're stepping through assembly code. Most people won't have to do that, but if you're digging into some like disassembly stuff or your the Go runtime and the Go project itself has a bunch of assembly and stuff like that. So if you're ever debugging that, this is useful. Another really useful command is call. So it allows you to call a function. Now this is something that's specific to Delve because it requires support with the Go runtime. So Delve actually coordinates with the Go runtime to be able to implement this feature. Currently, it's only supported on the Linux AMD 64 backend for Delve, but we're working to increase that support to other operating systems and architectures. The trick there is that the coordination that we have to do with the runtime is very, very low level and is implemented in assembly as such. So it's very architecture dependent. So we're working with upstream Go to continue to port that to other, like I said, operating systems and CPU architectures. So there is some limitations. I won't go through everything here now, but when you're in a Delve session, you can write help call and get more information there. So to call a function, the syntax is pretty simple. Just call and then the function that you want to call, provided arguments that you want to pass to it, and then you'll see Delve will execute that function for you and then show you the values that are returned. I like this feature a lot because it makes the debugging session feel like interactive instead of so like you're just looking from the outside in. It kind of makes you feel a little bit more like you're interacting with your program, which is something that I really like when I'm debugging something. Okay, another command that you'll likely use a lot is restart. So let's say you've ran your program, you've ran it all the way to the end, but you still haven't figured out your bug. Restart will allow you to restart your program from the beginning without exiting the debug session. If you're debugging a recorded program, which we'll talk a little bit more about later, you can also restart from a specific checkpoint. So this is convenient if you don't want to go all the way back to the beginning of the execution of your program. You can set a specific checkpoint and you can restart from there as many times as you want. With this restart command, you can also specify new command line arguments and input file redirections. So this is useful for if you just want to reinvoke your program with different arguments to see what's going on or help your debugging session. This is a very useful way to do it, and you don't have to jump outside of the debugger. So the syntax is really simple. Just restart, and you'll get some output saying that it was restarted and the new process ID. Right, now let's move on to inspecting and modifying program state. So you're in a debug session, you want to kind of see what's going on. So how do you do that? I won't go through everything explicitly here because there's about 15 minutes for each section. But if you look through, you see a bunch of different commands. So args, locals, print, vars, so on and so forth. So here's kind of a breakdown of what each one does. And if you want, if you're watching at home, you can kind of take a picture of this or something. Or the help command, once you're in a debug session, also breaks down commands by section of like what they groups them together by functionality. So you can get a lot of this information from there as well. But these are just all the ways that you can kind of inspect what's going on. And a lot of them are convenience, like args will print all of the function arguments, locals will print all the local variables, and then you can use print to dive in and say, like, I want to print the value of a specific variable. You can also see the value of the CPU registers, and you can also examine raw memory as well. And finally, something that's super useful, and again, kind of goes back to making the debug session feel interactive, is to be able to set the value of a variable. So Delve allows you that ability as well. All right, we're getting towards the end of this first section, so let's talk a little bit about navigating your program. Threads and Goroutines. So your Go process is made up of threads and Goroutines. How do we inspect them and how do we move around them? Also, apologies if I'm like double clicking or something like that. The slide progression is acting a little funny for me right now. So let's talk about how to examine threads and goroutines. So the two commands that you're going to want to use, very self-explanatory, threads and goroutines. Very easy to remember. List threads, put threads. It'll list all of the threads that are running in your program and where they're stopped at. There's different commands that you can use to control the output of this. So I encourage you to write help threads in a debug session. And additionally, to list goroutines, use the goroutines command. This will list out all the goroutines running currently and also where they are and what thread that goroutine happens to be running at, and some information about the goroutine, like its status. Again, there's a lot of flags and things like that that you can use to control the output of goroutines. So I encourage you to type help goroutines for more information on that. To switch between threads and goroutines, you can use the singular version of that plural, just thread and goroutine. So what this allows you to do is, if you want to inspect what's happening on another thread and switch your debug context there, you can do that really simply. Just say thread and pass the ID of the thread that you want to switch to. It'll show you switch from one thread to another, and then your execution context will then be in that thread. So if you do like list to show the source code, you'll see where that thread is at instead of where you were prior. The same works for goroutines. So if you want to switch to a specific goroutine, just provide the ID that you would have gotten out of the goroutines command, which listed all of them, and then you can see that we switch from one goroutine to the other, and it tells you what thread you're now executing on as well. Another convenience is if you don't want to switch your entire session to another goroutine, what you can do is you can just execute a single command in the context of that goroutine, but while staying in the context that you're at. So this can be super useful, and the syntax for that is just goroutine, the goroutine number, and then the command that you want to execute. So you can see we are on goroutine. If we were back on goroutine 0 or 1 or something else, we want to list where the source. We want to see where the other goroutine is stopped at in the source code. So we can just do goroutine to list, and it'll kind of output that information for us. Okay, so now let's talk about a little bit more, dive into a little bit more about what you can do with some of these commands. So, as I mentioned, a lot of these commands have flags and things that alter their behavior. So I won't go through all of this, but this will kind of optionally show you more information or change the display of the output. So I encourage you, again, to type help in goroutines and read through this information so that you kind of have it in your toolbox. Something that is super useful, though, is to be able to filter goroutines. So say you have, 100, 200 goroutines running in your Go program. The goroutines command by itself isn't going to be that useful because it's, 300 lines of output is not going to be all that useful. And Delve will by default truncate anyways. So let's say you only want to see the goroutines that are executing a certain location. So you can use the with flag and provide a location for filtering. And then that'll show you only goroutines that are executing within the main.go source file. You can also filter by label. So if you're not familiar, you can assign labels to goroutines. And so if you wanted to filter, like, I only want to see, the goroutines running this specific job, and that's marked, those goroutines are marked with a label, you can filter that way as well. You can also filter by the running state of the goroutine. So I only want to see running goroutines. That's a good way to filter it as well. It gets rid of a lot of stuff. And then user versus runtime goroutines. So this is like, I only want to see the goroutines that are actively executing what we call like user space code. So not in the Go runtime. That's another really, really useful filter that you can do. There's more information on this, again, through the help command, through a debug session. So I would encourage anybody listening to explore that as well. But it's something that I just kind of wanted to make everybody aware of. Likewise, we can also group. So we can group by location and group by label. So these are also, like, if you have a ton of Goroutines, this is a really easy way to kind of parse that output at the command line. So once you're in a debug session, sometimes you want to see like the stack trace, right? Like, how did I get to this function that I'm at? So stack alias BT will print out the stack trace for the current function that you're at. So if we continue to main call me, and then we execute the stack command, you can see we're in main call me, which was called by main, which was called by runtime main, which was called, so on and so forth. So this is really, really useful just to be able to see how you got to where you're at. And then with this, we can also print out, within that stack trace, we can also print out all of the defers within that stack. So any functions that the current function is deferred, and any deferred function up and down the call stack. So here you can see backtrace with defer. We can see we do have a deferred function. We have a deferred fumped println call. You can see where it was deferred and all of this stuff. So it provides a lot of useful information for that. Just another way to kind of really examine what's going on in your program. Now that we have information about the stack, let's talk about how we can kind of move around it a little bit. So let's say you're in a function, but you wanted to see what happened in the function that called the function that you're currently in right now. You can use some of these commands. So you can say frame to switch to a specific frame number. So when we did the stack command, you can see the numbers that were on the left-hand side. Those are the frame numbers. So you can use that with this command. And you can also do a one-off, kind of like we showed earlier, of I just want to execute a specific function or a specific command within the context of this frame. You can do it that way. Up and down are just convenience methods for going up one frame and similarly down one frame. And then deferred allows you to execute a command within the context of a specific deferred call. So specifically, if you want to inspect what's going on in a function, but you only want this this command to trigger specifically in the context of when that function has been called via defer, this is a way to do it as well. And this kind of pairs up nicely with what I showed just before of printing out all the deferred functions up and down the stack. All right, so with that, I think we're ready for kind of our midway break. Let me stop the share real quick, and I will reshare to the quiz. So we're gonna have some quiz questions based off of some of the stuff that we've presented so far. So if everybody's ready, I will go ahead and start the quiz. I think that there is. I've
just started that for you, Derek. So everyone will just log themselves in, and then once everyone's logged in, just hit start quiz.
Perfect.
Cool.
Let's see. Should I go ahead and hit start quiz now, or give people a little bit more time?
Yeah, go for it. Some people just like to watch, so I reckon.
All right.
Start up.
Let's go ahead and get started. So what subcommand is used to start a debug session without an existing binary? This actually could be, you could make an argument that some of these others could be a correct answer, but there's one that is explicitly not the correct answer. Okay. I think our time is up, so I think I just click on the correct answer button. So the correct answer is debug. That it's also true that you can do it with trace and somewhat attach, not so much because you already have to have an existing binary that's running. But all right, let's move on to the next question. So what flags does Delve pass to the Go compiler when building your program?
I think it's BJ.
All right. Results are in. Let's see. Correct answer is GC flags all-n-l. And again, this is to disable compiler optimizations. So how long ago was Delve started? Right. Most people got this right. It is 7 years, creeping up on 8 years ago. And again, I'm sorry if anybody can hear like the drilling and stuff that's happening in the background. Okay, so what is the argument you must supply to the trace subcommand?
BJ.
Right. Results are in. The correct answer is regular expression. Now let's see. All right, we got a few 100%ers.
Wow. Nice. Very good scores there. Nice. Wonderful. So there's a prize going out there. 2 prizes actually. It's joint top. We'll have 2 prizes. Or will we? Yeah, we will. Cool. Right, back to you. Sorry. There you go.
All right, so I'll go ahead and finish the quiz there. All right, there's a nice little break. Let me go ahead and stop the share and then go back to sharing my slides. And I will endeavor to get through these pretty quickly because I think I went a bit over time on the first part. Okay, let's see. Okay, so now let's get into some more advanced concepts. The first thing I'd like to talk about is disassembling your code to see the actual CPU instructions that are produced in the binary. So very simple. You can just use the disassemble command. Delve has its own internal disassembler that can kind of read the actual raw bytes and turn those into CPU, like kind of human readable CPU instructions. So you can see we're stopped in this function called call me, and by default disassemble will disassemble where you're currently at. So we can see we're in main.callme within the main.go file. The output there, you can see the file and the line that we're stopped at. And you can see all of the addresses of the instructions. And then all the way to the right, you can see the actual CPU instructions that are being used. So like load effective address, compare, sub, move, all of this stuff. You can also disassemble a specific location by passing the -L flag and then a location. So like main.go 12. So just briefly, disassembling is something that I think most people won't have to do that often, but when you really, really need to dig down into what is your code doing and what is it actually doing at the CPU instruction level, this can be really, really helpful to figure out just what's really, really going on. Another feature that I'd like to talk about is setting watch points. So watch points are similar to a breakpoint. However, a watch point will specifically kind of watch for changes to memory and stop when something like that is triggered. So, for example, if you wanna set a watch point, like you want to stop the program execution anytime a variable is read from or written to, or modified in any way, right? This is the command that you would use to do that. So it's useful for watching a specific variable and modifications to that variable. So if you want to watch reads, just watch -R and then the name of the variable that you want to watch. And the name of that variable is within the current context that you're in right now. So it has to be a variable that you could print out or something like that. So Delve knows where to find it. If you want to watch writes, similarly, watch -W and then the name of your variable. And then if you want to watch any kind of, like any time that variable is read or written to, you can do RW. And then this is just a really super like useful convenience thing of like, I'm not really sure where I want to stop, but I want to stop anytime that this variable is modified or this particular area of memory is modified. This is just a super helpful way to do that. Okay, so we're getting into, I think, the last two topics, which is perfect time-wise. So the last two topics, this one especially is something that I'm really excited about. So deterministic debugging is, just to kind of explain it a little bit, deterministic debugging or record replay debugging is a method that allows you to record the execution of your program. So record all the non-deterministic events that happen during the execution of your program and then replay that back faithfully. So this is really useful for, like, say you have a bug that only shows up once every 100 runs or something like that. Like, it shows up very, very infrequently. You can use this method to record the execution of your program. And if you can capture and record the bug happening once, you can replay that back indefinitely. So you don't have to run it another 100 times just to trigger that bug again. Once you've captured it in a recording, you can play that back as many times as you want. You'll always hit that bug every single time. So it's a way to deterministically reproduce failures in your code that might be intermittent. So it's really good for debugging flaky or intermittent failures. There are some downsides though. So right now, as of right now, Delve uses another program called RR, which came out of Mozilla. It's a record and replay debugger. So Delve uses that for the time being as its backend for record replay debugging. And one limitation of RR itself is that it runs the program that is recording single-threaded. So for Go programs, this has more of an overhead in terms of performance, right? Because a lot of Go programs are by nature very, very multi-threaded and very highly parallel. So this can be a performance hit, and this isn't, in its current implementation, this is not as useful for debugging like race conditions and things like that, because your program will be run single-threaded. And this is just a limitation for right now. We're working on some things to improve this in the future and continue to improve the record and replay debugging ecosystem. So definitely keep an eye on this and what is going to come out in the future. But a cool thing about this is the recording can be shared. So once you capture that recording, you can then take that like artifact that's on disk and you can pass it around to other engineers on your team, and it kind of makes it a little bit more collaborative. But also you can kind of be like, hey, I don't know how to solve this bug. Maybe another engineer or somebody on your team does. You can just hand them this recording, and with that, they have all of the context that they need to be able to debug that failure, and they'll be seeing the exact same series of events that you saw on your machine. So super, super useful. One other caveat of it right now as well is that it only works on Linux machines. So that is just one caveat for the time being. So I want to play a small example of this in action that I have pre-recorded. So here's kind of an example program. We can see it's doing a lot of things that should be non-deterministic. Like they should be different each time the program runs. So we get the current time, we print that out. We execute a command. We run the date program. We get the output of that. And then we print the output of the date command. We also print the output of the PID of the process that we're executing. And then we also read from dev random. So as we know, this should be random and different every single time. So we read the output of dev random and we print that out. So this is just kind of giving examples of all of this stuff that should be different every time you run or debug your program. And we'll kind of see through this example how the record replace stuff works. So you can see we run the program, we get the PID, the date, a bunch of random bytes, all kinds of stuff. And you can see every time we run it, the output is just, slightly different. The PID changes, the time changes, the random bytes change. All of this stuff is different every single run, as you would expect. Now, let's see what happens when we debug this using the record replay backend. So you can see some output there where the recording trace was stored, and then you can see some initial output from the program having been run. So what happens is we run the program initially all the way through, and we record it. And then after that, Delve will jump you into a debug session where you're debugging that recording. So we're at the top, we continue. We can see that the output that we just saw matches the initial output that we saw when the program was run all the way through. And then when we restart the program to the very beginning and continue again, we see, again, the output is exactly the same. The PID is going to be exactly the same, the date, the random bytes that we get. So every time we replay this program, this recording, it's always going to be exactly the same. Yeah, and this is just something that I think is just really, really cool and really exciting. I use it a lot. And again, there's a lot of limitations for it right now, but definitely kind of look forward to some exciting advancements to this in the future. All right, okay. The next topic that I want to talk about is scripting Delve. So this kind of unlocks a lot of the power of Delve at kind of a lower level. So Delve uses the Starlark scripting language, which is a Python kind of like variant. It's very similar to the Python syntax if you're familiar with it. So this kind of allows you to create your own commands. So Delve by default provides a lot of really powerful commands, but if there's something missing that you want, you can load these scripts into Delve, and then they become essentially first-class commands in your debug session that you can execute. Similar to how you would execute in like the break command or threads or anything like that. It becomes kind of a first. It just allows you to kind of make your own commands and that kind of thing. So all of the anything that you would have available through the RPC API that Delve exposes, you would have available to you as well through the scripting language. So you can pretty much do anything that Delve can do internally, you can do through the scripting language. So it's really, really powerful. You get access to a lot of kind of internal features of Delve that you can kind of use and stitch together to make really, truly powerful commands. So here's an example of a command that you could write. So anything prefixed with command will be shown as a command in your debug session. So here we define a command called flaky. And what it does is it will repeatedly run the target program using the RR backend until a specific breakpoint is hit. So this is really useful for in the context of what I was saying earlier. Like if you have a bug that maybe only gets hit one every 100 times, this command, all you have to do is write flaky when you're in a debug session, and it will continually rerun your program and record it. Only stopping when it hits a specific condition. So instead of you manually doing this 100 times or however long it takes, you can write a script and let the computer do the work for you. So this is just one example, and you can see the Python syntax and all this stuff, but I would encourage anybody to look into this a little bit more. We have some documentation specifically in the repo that covers how to script delve. Again, super, super powerful feature, more of an advanced concept and more of like a power user feature, but when you need it, you really need it, and for delve, it's there. So yeah, really exciting feature. Okay, now the last kind of example that I wanted to run through is more of like a practical example, something that you don't see as often, but Kubernetes is all of the rage in a lot of places right now. And so what do you need to do, or what do you do when you need to debug something that's running like in Kubernetes or somewhere like that in that environment? So with newer versions of Kubernetes, there is the kubectl debug subcommand. So it's been available since Kubernetes v1.18. It allows you to create an ephemeral debug container. So you do need ephemeral container support. And this is something that you have to specifically, I think for right now, you still have to specifically enable in your cluster. So you should be aware of that. The Kubernetes documentation goes through all of how to do that. If you're curious and you need to enable that. And so the debug container that's created in your cluster is in the process namespace, or the PID namespace of, that should be PID namespace. It's in the PID namespace of the process that you're trying to debug, and that allows you to attach to a program running using like the delve attach command. So you can create one of these debug. You can create your own container image that already has delve in it, and you can use that to create a ephemeral container in your cluster to debug a program that's running in cluster. So again, I have a short little demo to show this in action. So I'll go ahead and start playing that now and talk everybody through it.
Yeah, it'd be huge.
So you can see on the left, we have just kind of like a small little, HTTP server. Has just a few endpoints, nothing too exciting there. And then on the right, we see we have basically just a few definitions of Kubernetes services. So we have our pod, we have our service, we have some ingress set up. All of the stuff that we need to be able to deploy our little test service and start debugging it. So here you can see we've exposed our service using a node port, so we can curl it locally, and you can see the service is running, it's responding. Now, I've already created an image that has delve in it, so you can see that in the image section, but we're using the kubectl debug subcommand, and then bam, just like that, we're in a delve prompt, and we're already attached to the process that's running in the cluster in this particular container. So once we start kind of examining what's going on, we can continue, we can see the service is now running because we've continued it. It's no longer stopped by the debugger. When we control C, we can stop the process and start examining it a little bit. So let's set a breakpoint on hello, which is one of our the little handlers that we wrote. Then when we hit that endpoint again with curl, you can see we hit that breakpoint. We're now stopped. Now when we're back in the debug session, when we try to list out the source code, we can see we can't find the source code because where the source code was compiled is different than where the source code might be in your in your container. So if you look at our debug container, we have delve copied in, and then we also copy in the source code of the program that we're trying to debug. So this is all contained within our little debug container. So while your container in production will likely just be like a scratch container that maybe literally only has the binary that you want to run, we can take the source code and copy it in our debug container and take that with us. And then we can use some features of Delve to be able to find where that source code lives and associate that with paths that are in the binary that we're trying to debug. So if we copy the location where it's at, the video kind of went fast, but you can see we used a command called config substitute path. Basically we're saying anytime you see this path, replace it with this one. And now when we execute the list command, you see we now have access to the source code where we previously didn't. All right, and that's the end of that example. So let me see. That's the end of the presentation. So I just want to say thank you again for everybody who came in to check this out. Thanks to the Go Naviro folks for inviting me to do this and speak to everybody. I really appreciate it. And if you want to reach out or ask any questions, my GitHub is listed there below, github.com, Derek Parker, and I am on Twitter at Dirk the Daring. Yeah, and that's it. Thank you so much.
Yeah, thanks, Derek. That was great, man. They were really thorough. A lot of really good content there, and some interesting stuff as well that we know the community are always asking about. That Kubernetes stuff at the end was great. So big thanks.
Yeah, huge thanks, Derek, and everyone that stayed on. I know we've run over a bit on time here, but hopefully you guys found a lot of value in that. And yeah, huge thanks, mate, for getting involved, and for everyone that signed on today. We will be making a recording with some timestamps and things like that after. I know there was some super useful stuff on there, so keep an eye out for that. And yeah, I mean, normally we do a bit of a Q&A, but I think in terms of timing, maybe we'll just run through the top question there submitted by Rajiv, who's our super winner today with the double scoop on the, I think he won the cards game as well. So a couple of prizes going out to you, mate. But if we could just run that one by you, Derek, before we finish up, which was when debugging Go programs built with the standard toolchain, which is better, which is the better tool, and why?
Sure. So I'm not super clear on exactly what the question is asking, but I will say when the program, so no matter what the program gets built by the standard Go toolchain, it's just whether or not we disable certain optimization. So like I mentioned, when Delve compiles your program, it compiles using the Go toolchain, just passing some flags to disable some of the optimizations. And as I mentioned, this is less and less of an issue as time goes on. This was more of an issue historically in older Go versions where they debug information that's present in the binaries that's produced. So without getting into too much detail, binary like ELF binaries and things like that have information in it that kind of helps debuggers figure out where things are, like variables and stuff like that. And in older Go versions, that information wasn't as thorough for optimized binaries. So it's more of a historical thing. It's still kind of preferable to run it specifically the way that Delve does with these optimizations disabled. But nowadays, debugging just a regular fully optimized binary, you'll have typically just as much success as you would otherwise.
Cool. Perfect. Yeah. All right. Well, look, there are a couple more questions. Maybe we can ping them over if you do get a chance to share your knowledge on them for the questions that were shared. That would be fantastic, Derek. Maybe ping you an email over with a few of those other ones that were asked. And again, yeah, huge thanks for your time. There was another quick shout out as well for the tech quiz winner. I think we had a joint winner exactly on timing and answers correct. So we'll be in touch with you guys as well. That was Alex and Raj Kumar. So cheers, guys, for taking part. And yeah, anything else, Joe?
No, guys, look, we're going to be posting up the video and the schedule of the other upcoming E-Series events, one before Christmas and one just after the New Year. So make sure you log on to the Go Naviro LinkedIn page, subscribe and get on the follows so that you can get updates straight to you and you don't miss out on any of the futures. But look, Derek, just want to say a really big thank you, man. It was really, really good talk, and we know the community will love to pick up on all of that.
All right, guys, take it easy. Hope you enjoy your day out there in the States and the evening for many of us around the world, and we'll catch you next time.
Bye, Derek. See you later, man. Thanks.
Thanks. Bye.